So thanks for the opportunity and for attending. I apologize to those of you who may have heard bits of this before. I've got a bit more hydrology, I guess, in this one, and I'm really interested to hear your perspective from the hydrological community on some of these topics. So as I said, I'm mainly at the Department of Meteorology at Reading. I have been for 10 years, but as of this spring, I now have a 30% appointment at the Julich Supercomputing Center. And I'll just click the wrong button there. Okay, so just the heart of the matter, I think, is climate risk involves three aspects. People mainly would agree. One is the random element of weather, or the chaotic aspect of weather. So you can think of it as internal variability and the extreme weather and climate events. Then you have the change in those possible states. And if you think of climate as being the PDF of all those possible states and all the relationships between them, then climate change is just the change in that PDF. And then you've got the human managed aspects of vulnerability and exposure. Now, people like numbers and people like probability. My sense, everyone wants probabilities, but my sense is that, well, we have to take probability seriously. And I think most people don't realize what they're asking for. I think they seem to think it's a very simple thing. As far as I know, the only, let's say, objective concept of probability is a frequentist or an aleatoric probability, where you have a well-defined chance process. And then everyone, I think, would agree on the outcome of that chance process because it follows a set of rules according to the axioms of probability. And that only applies to internal variability. It obviously doesn't apply to climate change itself, unless you have an idea of multiple universes and we're just one universe by chance out of many. But if we don't go there, then basically, of course, the human managed aspect is decision. So really, it's only the internal variability which has a hope of being described as a chance process. And even that may be highly uncertain for the most extreme events. The second is subject to epistemic uncertainty or systematic uncertainty or uncertainty in knowledge. And of course, we have the climate forcing is uncertain, but even for a given climate forcing, there's considerable epistemic uncertainty in the climate response, and I'll talk about that. And then the third, the human managed aspect, of course, that's uncertain too, and it needs to be cast in a decision space. And to cast something in a decision space means you need to have the concept of causality, because you have to tie a decision to an outcome, and counterfactuals. What if you did this versus that, and so on. And those are concepts, causality and counterfactuals are concepts that don't apply in the aleatoric probability treatment. If you look in a textbook on probability or classic textbooks in weather and climate, you don't find any of those concepts. And ultimately, probability is degree of belief. And you can actually formulate in probability theory the entire axioms of probability in terms of actually preferences or action. Savage from the 1950s famously did that, and Frank Ramsey earlier. So in fact, probability is inherently subjective. So the challenge, people have to accept, hey, well, that's what I believe, and we can discuss that if you don't agree, but it's a bit of, it takes a lot of, certainly in climate science, this takes people out of their comfort zone a lot. So our challenge, though, is to acknowledge this and then develop a scientific language for meaningfully representing and communicating this complex web of uncertainty. And in doing so, we have to combine multiple lines of evidence and extend it into the decision phase. So that's our charge. And I think we have to take it seriously. Now, you can ask whether narratives or storylines are a good basis for decision making. And I can still tell this joke, I guess, because this man is still the prime minister. So two years ago, when a little bit more in the spring, when things were melting down in Britain as far as COVID was concerned, apparently his advisor said, we have to have an emergency meeting and discuss what to do about COVID. And apparently Boris said, but it's Wednesday. I'm going to see the Queen. I go to see her every Wednesday. Sod it. I'm going to go and see her. And his advisor, according to this advisor's word, that's why I call it apocryphal, because no one completely trusts the this man apparently said, you can't go and see the Queen. What if you go and you give her coronavirus? And apparently, according to Dominic Cummings' bar, said, you're right, I can't go. So that's a narrative. There's no quantification, no probability. It was probably a very good argument. I don't think it was the wrong argument. So statistics is a big part of this. I'm not going to give a talk on statistics. That's a different talk. But I'll just mention it in passing here. So, of course, you'll be aware that the concept of statistical significance, which originates in frequentist practice, has been criticized a lot over the years, decades, really. This is an essay from Nature just over 3 years ago saying we should abolish statistical significance. It would make science harder, but it would make it better. So I've written, I published an essay last autumn on that in climatic change, arising from a workshop with philosophers of science, in fact. And so I talked about some of these points. An obvious point that the Nature editorial makes is that, of course, the p-value less than some threshold like 0.05 should not be interpreted as a true-false statement. I mean, that's very clear, but it's ignored widely. But the issue runs much deeper than that, and of course, it's arisen in lots of fields, psychology and so on. I think in climate science, we have different kinds of issues too, because climate change science is anchored in physical understanding. Yet the practices of frequentist statistical practice absolutely dominate published climate change science, and it's real obstacle for us, I think, at the time, because frequentist approaches have no place to bring in physical reasoning, no ability to talk about the probability of a physical hypothesis being true. So there's a disconnect between physical reasoning practice, and I talk about that in the essay. So I just refer you to that. It'll come up tangentially in what I'm talking about, and we can talk about that in the questions as well. So why do we need storylines, physical climate storylines, and I'll define them shortly. The basic reason is that climate models disagree on the nature of the atmospheric circulation response to global warming. Of course, we have the same issues for climate sensitivity, for things like West Antarctic ice sheet collapse, for tipping points. You could certainly talk about storylines, and people do, in fact, in those areas. But my own interest is in the regional response to climate change, which is mediated by the atmospheric circulation. So this is just 4 models from CMIP-5, but I think it's pretty much the same story with CMIP-6. These are just 4 of the models. The end of century response under RCP 8.5 to climate change. It's the lower tropospheric, it's the 850 hectopascal zonal wind speed, and you can see the climatology is in the contours. You see the North Atlantic jet, and then you have the change in the colors. And each of these models had a small ensemble, so there was some sort of significance estimate for those ensembles, which is a legitimate use of significance. And you can see that they vary a lot, and especially over Central and Northern Europe, the sign is opposite between many of the models, and the features are happening in different regions. So if you average over this, you're going to get a very washed out response, and yet which of them might be true has direct implications for precipitation and droughts and heat waves and so on. And if you average it, as I said, it doesn't really have any physical meaning, because all the models say something's going to happen. None of the models say nothing's going to happen. Sorry, I keep clicking the wrong thing. Now, because of that uncertainty in the atmospheric circulation response, there's an uncertainty in the precipitation response in many regions. This is in contrast with regional warming, where you get unambiguous predictions of warming over sufficiently long timescales in all regions of the planet. But in this case, this is an IPCC style figure for CMIP-6 now. This is boreal summer, extended summer, and the dark stippling, the full stippling, is the IPCC type stippling where the models agree on the sign of the change. So it's robustness in sign. They could still differ in magnitude. And we introduce here an open stippling, which is where the models indicate the potential for a large but non-robustly projected change based on a chi-square test. And you see that the open stippling is over many tropical regions. So just to give an example, in the middle panel on the right-hand side, you have Singapore, where the models have a tendency towards drying, but some models could be drying a lot and some actually wetting, versus Sao Paulo, which is the opposite, where the models show a tendency towards wetting, but some have a lot of wetting and some could actually be drying. Right. Now, in most extreme events, the role of unusual dynamical conditions is generally a very important causal factor. So this is a case of a fire risk index. This is from a paper from 2021 led by Yunpa Lim at the Australian Bureau of Meteorology. The paper was actually on the prediction of the early breakdown of the stratospheric polar vortex that year. But as part of the paper, there was an implication for the wildfire season, and this is the operational fire risk index used in Australia, and you can see that it was a higher fire risk that season. You can see that the four panels are a multilinear regression approximation to that, which doesn't work so well in Northwest Australia, but in the eastern part seems to match quite well, which was the area of concern there. And you see that the warming trend is a pretty small contribution. And the major contributions were three circulation-related effects, which all had to do with drying and winds. One was the vortex, was the breakdown of the polar vortex, stratospheric polar vortex. Then there's Indian SST anomalies and Pacific SST anomalies, and they all conspired to create a perfect storm. So if you just attribute it to warming by marginalizing over all these other factors, which is generally what happens in a probabilistic extreme event attribution, you're really not capturing much of the event there. The thing is, we don't really know how many of these factors are going to change under climate change. We have some ideas maybe for the polar vortex, but I think the Indian and Pacific SSTs, we don't. So it's important to bear those in mind, that those were important factors and they could change in the future. Now, climate scientists tend to describe changes in extreme events probabilistically, and to be probabilistic, you have to aggregate, of course, and I mean a frequentist probability. So this is from the SPM of the AR6 report, working group 1 report, where it talks about changes probabilistically of heavy precipitation over land or drought in drying regions, expressed either as a change in intensity for a 10-year event, or as a change in frequency for the 10-year, for a magnitude corresponding to a 10-year event in pre-industrial times. But this is statements for the entire globe, either over land or in the drying regions. But in general, in IPCC, the uncertainty around dynamical aspects of change is managed through generalization. For example, a focus on zonally average quantities. You can find lots of statements on zonally average quantities, but generalization can be locally misleading. The fundamental problem when you generalize is you're aggregating over things that are not the same. So you have a potential confounding effect from that structural factor. And that's just Simpson's paradox, or Joule-Simpson effect, and you can get erroneous results because of that, because of a confounder. And this happens a lot in climate science publications. In this case, this is just showing from Julia Minland's work. She's a PhD student with me at the University of Buenos Aires. The change in precipitation from the CMIP models from a strengthening of the southern annular mode, and you can see that if the SAM change is induced by tropical warming, which is shown on the left, it tends to be drying. But if it's induced by delay in the breakdown of the stratospheric polar vortex, shown on the right, it tends to a wetting. And that's because one corresponds to a strengthening of the westerly and one in the other to a poleward shift. So just treating that as a SAM index is combining two very different things that really shouldn't be combined. So at the regional scale, when you do this probabilistic attribution, and this is another figure from the SPM of the Working Group 1 report, you're challenged by the uncertainties in model projections, the fact that I've just said the models may give different different signs have changed, so we don't even know in what direction things are necessarily moving, or by lack of verifying data. So the first of those is shown in the hatching, the light gray hatching, and the second is shown in the solid gray. And that really limits what can be said about drought in many parts of the world. And you can see that a large part of the world is covered by one or the other. So the other thing that's important is that how we do our science actually is shaped by contextual values or social values, or sometimes called non-epistemic values. There's quite a literature on this in philosophy of science going back several decades. I don't think it's completely percolated yet into climate science, although it's starting to, and there are a few papers on this. This is one led by Chris Jack and some colleagues. It's in revision in BAMS, I think should go through, which is why I'm showing it here. So we talk about 6 different case studies of different kinds of analyses, multi-model ensembles and so on. And we talk about how the different contextual values enter in, and how those shape what are known as the cognitive values. So the cognitive value, or sometimes epistemic value, are the values that are truth conducive, that are essentially good values. Cognitive values, they're all good. They're all in the benefit of truth. But the way that which ones you tend to favor depends on contextual values. So we found that in many cases we could group things into these 2 options. It covers a lot of things. If your contextual values are the norms of practice, the ease of publishing, getting your career ahead, that tends to encourage a cognitive value of reliability. In other words, not being wrong. And reliability is guarding against false alarms or type 1 errors. That will tend to guide conservative methodological choices. And then those will be unaligned with another cognitive value, which is valuable too, which is informativeness. And informativeness is guarding against miswarnings. There are different words used in different communities, but you find this, it's in the psychology literature. So the general concept of reliability and informativeness is a very general concept across many types of science. And broadly speaking, it's guarding against type 1 or type 2 errors. So there's a values tension between those 2. And in the panel on the left, these contextual values, which are the orthodox ones, I would say, tend to favor reliability over informativeness. On the other hand, if the contextual values were societal benefit, perhaps funding priorities, which are trying to target societally relevant problems, or reducing uncertainty, those are going to guide a cognitive value of informativeness. That will tend towards more subjective methodological choices like model selection and so on. That will then create a tension between reliability. So we just have to recognize this, and that our choices are not cast in stone. They reflect contextual values that we choose to prioritize. So here's an example. I published a recent perspective in PNAS Nexus, the first issue of the journal, with Regina Rodriguez, an oceanographer from Brazil. And as a case study there, we talked about the failure of the 2013-2014 South American monsoon. So the panel in the upper left is the climatological setup with flow off the Amazon in the South Atlantic convergence zone. It's very important for southeast of Brazil, which is the economic hub of Brazil. But in this particular summer, there was a blocking anticyclone that cut off the precipitation flow, led to drying over that region, as you can see here. And also because of the clear skies induced high temperatures shown here with the wind. And you can see images of the dried out reservoirs. It affected hydropower, it affected water security, agriculture, and also fisheries. And so we had a classic correlated risk in the food, water, energy nexus. There was an event attribution study of that using the probabilistic method, which is the main method used, and published in the special issue of BAMS on extreme event attribution. They calculated as a risk ratio relative to pre-industrial. So greater than 1 means that climate change increased drought risk, less than 1 means decreased drought risk. it's a long scale here. You can see that the observational database here, GPCC, showed a tendency towards increased drought risk. The my 5 models for what they're worst also showed an increased drought risk, but the 2 versions of the Met Office model that were used here showed a decrease. So they pooled the error bars and couldn't reject the null hypothesis and argued that was insufficient evidence that climate change increased drought risk. But they're using a criterion of insufficiency, which is rejection of the null hypothesis, using a pooling of the uncertainties that assumes that all the estimates are unbiased, which doesn't seem like a plausible assumption. So we can ask insufficient for whom? If you were a water manager with one of these sectors, I think you would be very concerned about drought risk in this region. So if you consider all the uncertainties in climate change, in the traditional way, it leads to what's been dubbed a cascade of uncertainty. This is quite a famous a depiction of that from Wilby and Desai's paper in 2010. There's other versions of this. The idea is that if you start from future society and construct scenarios of greenhouse gas emissions and climate models and regional scenarios, impact models and so on, you just get this ever increasing cascade, and we have to navigate this somehow. We actually have a huge amount of climate information, even if not more, at the local scale, both from observations and modeling. It's just that the information is conditional. So this example I'd like to show from the 2003 heat wave in central France. The part of France is shown in this little black square here. You can see from the scale here, it's about 3 kilometers square. So the top panels show the vegetation index, the NDVI, where red is living and green is dead. The bottom panels show surface temperature. There's a different scale in the 2 years. The column on the left is 1 day in August of 2000, and the column on the right is 1 day in August 2003. So you might say, how can I compare 1 day in one day in 1 year with 1 day in another year? Surely I would be killed by just internal variability. And it's true that you shouldn't look at the absolute difference between the 2 panels, but you can look at the relative difference across the scene. And you see that in the heat wave summer, the forest, which is shown in the red patch here on the right, is still there. There's a few hedgerows still there as well, but all the pastures and grasslands have died out. And if you look at the temperature difference between the 2 panels, it's only 11 degrees C in the forested area, but 20 degrees C in the areas where the grasslands have died out. And this contrast is extremely sharp. You see it over 100 meters. That's not synoptic variability. That's to do with the land surface feedback, of course. So we understand this. It can be modeled. It can be observed very well. So we may not be able to predict the statistics of heat waves in the future, but we can predict their implications and how to manage their impacts, as long as we treat the information in conditional form. So scientists are pressured to issue single definitive statements. That's how it was characterized by Andy Sterling in an essay in 2010 in Nature. And he argued we need a language for expressing a plural conditional state of knowledge, if that's what it is. Obviously, if we have a single definitive statement that is informative, then that's fine. But what tends to happen in assessments, for example, like IPCC, is that the scientists are forced to craft single definitive statements, and that forces them into rather uninformative statements. And whereas if we embrace the fact that the knowledge is actually plural conditional, then we can do a lot more with it. And as you probably all know, in hydrology, there's many decision-making methods that deal with deep uncertainty. And so this is not really an impediment to usage. In fact, it may help usage. So this led to the idea of storylines. Of course, it's not a new idea, but in this paper, which was with about 20 authors following a workshop in Britain, we came up with this paper and came up with a definition that storylines were physically based unfoldings. These are physical climate storylines, of course, physical based unfoldings of past weather or climate events or future events or pathways. And this definition is now basically incorporated in the IPCC glossary, and there's a box on it in chapter 10 of the Working Group 1 report. The example that we used there was this unforecasted rain on snow event in the Swiss Alps. I won't go through it in detail, but there was it was in the autumn. a cold front came through, dumped a meter of snow in this part of the Alps. Then a warm front came through and there was an atmospheric river tucked behind it. So the snow melted, you had the rain on snow. On top of that, there was a local circulation, a cedar feeder circulation below the resolution of the forecast model. So it wasn't forecast by the weather forecast models. But of course, this is not a mysterious phenomenon. It's a well understood meteorological phenomenon. There's good measurements across the valley and everything adds up. So we talked about the different typologies of use, because this led to a landslide which cut off the mudslide, which cut off a village in a valley from the outside world for a while. So storylines are a way to navigate the cascade of uncertainty that I talked about earlier. And as I said, conditionality is crucial to that. So causal networks are a way to represent conditional information. They're a special form of Bayesian networks. So they're defined through these linkages which represent conditional probabilities. And so storylines can just be seen as instantiations of a causal network by conditioning on one or more nodes, for example, global warming levels and dynamical conditions, and I'll give examples of that. So the uncertainty space is represented discretely. In principle, there's nothing, if you had a causal network, you could generate probabilities, but they would be fundamentally Bayesian, and you would have to acknowledge that. That could be done, but as a starting point, I think it's good to lay out, to explore the uncertainty landscape through storylines, and you can think of then of representing the uncertainty space discretely rather than through a continuous probability. And the advantage of this is it builds in self-consistency, because your conditions will affect everything in the same way then, and that's really essential for consideration of correlated risk. Whereas if you aggregate and treat probabilities of essentially univariate or at most bivariate quantities, then it's really a struggle to represent correlated risk that way. Now, just one equation here. It's actually not. I assume you know a little bit about probability. It's a very simple equation. It follows from the axioms of probability, but I think it's quite a profound one conceptually. We tend to think of an event like a drought or a rain on snow event as being it will arise from a particular setup in the atmospheric circulation. So you can think of a joint probability of the event of interest, which is E, and the C is the circulation regime conducive to that event. So it's a joint probability of E and C. And then we have a subscript 1 or 0, which could be 1 being the future, 0 being present day. For example, could be P1 is present day, P0 is pre-industrial. But you get a risk ratio then. And from the laws of probability, the joint probability of E and C is just the conditional probability of E given C times the probability of C. So you see that this risk ratio of the joint probability factorizes into 2 terms. And this was in a National Academy of Sciences report, US Academy of Sciences on extreme event attribution from 2016 that I was part of. And so the first of the terms on the right-hand side is the ratio of conditional probabilities, and that's basically what is the change in probability of the event of interest conditional on the circulation regime. So it's essentially the effect of climate change for a given circulation regime. That builds in a lot of what we know with confidence about climate change. You know, where the fact it's warmer, the fact the air holds more moisture, and so on. It's sometimes called the thermodynamic component of change. You can define it in various ways. It's not a precise definition, but it's very useful. And the second factor here is a risk ratio of how the circulation itself might change. So that can be considered the dynamical aspect of change. And I've argued that should be treated separately, for example, by storylines. So if you combine these things together, you're losing the informativeness that comes from the fact that we can make very strong statements about the first of these terms, but much weaker statements about the second of these terms. If you pool them, then you're forced to make a weak statement, and that's probably not good from a communications point of view. So in many cases, the internal variability is really dominated by the dynamical component and the forced response by the thermodynamic component. This is from a paper from Clara Deser and colleagues using the NCAR large ensemble. So what they've done here, this is a single model large ensemble. It's the wintertime surface air temperature changes over 50 years. So the observed change is shown in the upper right here. And then they partition that into what they call dynamical and thermodynamic, which is based on, they basically look for correlations between the surface air temperature and sea level pressure, and they regress out all the temperature changes which are coherent with sea level pressure changes, and that's the dynamical part, and what's left is the thermodynamic, the residual. So you see, they actually have somewhat something in common here, but there's a difference because the dynamical part, for example, has a dipole where you get colder temperatures over Labrador and warmer over western part of Canada here. And then they use a climate model to define what the forced response is. It's a large ensemble model, and then they can make, according to that model anyway, they can then partition the observed change into internal variability and forced variability. And you can see that the observed change, they divide roughly half into the dynamic and thermodynamic changes, and the dynamic change is due to internal variability over that period, and the thermodynamic change is due to the forced response, and these other parts are really weak. So assuming that the forced dynamical response is zero is not an unreasonable null hypothesis. If you have reasons to believe something different, then you should of course bring that in, but it's not a crazy idea. So this brings me to the idea of an event storyline. So in this picture, I think this is more or less the same. Well, it is based on the figure in my paper in 2019. It's part of this box now in IPCC. So what's been happened is the dynamical conditions are split into remote drivers, things like Pacific SST anomalies, let's say, and dynamical conditions could be a circulation index. So you start on the left, you have climate sensitivity and greenhouse gas emissions, gives you a certain global warming level that'll lead to a regional warming level, which is pretty well understood, land ocean contrast and so on. Then you have remote drivers, which are less well understood, and those will lead to dynamical conditions. So if you condition on the dynamical conditions and regional warming, you basically block the influence of all these other factors, and you say what is the hazard that we get from that combination, and then you can talk about the impact, and the human element, which is in the gray here, is a causal factor in terms of the impact, and that's very important for decision making. So here's some examples. This is from a paper led by a PhD student of mine in Hamburg, who's just finishing up actually and has her defense next week, Linda Van Garderen. So this is imposing the observed conditions in a climate model with warmer ocean temperatures and increased greenhouse gas concentrations to essentially fill in the physics. This has a long legacy in the regional climate modeling community, what's called the pseudo global warming method. In that case, it would, in a regional climate model, it would be imposed through the boundary conditions. In this case, we have a global model, and we impose it through spectral nudging up to T20, so just the long waves. And the advantage of doing this kind of thing, conditioning, is that you can allow the use of weather resolving atmospheric models because it's very cheap to do. And that means you have a much more physically self-consistent event. For example, this was for the Russian heat wave of 2010, which was connected with a blocking event. You don't tend to get climate models to even be able to simulate an event like that. So when you do it in this nudged way or constrained way, you can at least follow the event of interest in its full realism. And also, quite importantly, I think, from a communication point of view, the probabilistic event attribution statements are very appealing because they give a number with error bars and so on, but they all those numbers depend very sensitively on the event definition, and the event definition is very arbitrary. Different users will have different concepts of the event. So although a number is nice, what that number might mean is completely unclear. in this approach, you remove the arbitrariness in the event definition. You just simulate the observed event with and without climate change, and a user can define it as they wish. This just shows a time series for the Russian heat wave of 2010, and you can see the blue are the factual runs with climate change. There's a small ensemble well separated from the red ones, which are the counterfactual. That's pre-industrial. You can see it would have been a heat wave above the climatology, even without climate change, but the climate change made it that much worse. This is a big box in space showing resolution and time. You can also get the same thing in space. So you get very high signal-to-noise ratio achieved in both space and time, and you could drive an impact model that way. Another example from Linda, and this was also with Julia Mindlin, they teamed up on this paper that was published in Weather, just came out, where they looked at the 2011-2012 drought in South America. Now, this shows they computed the potential evapotranspiration (PET), which is a measure of the water demand from the atmosphere. And as you can see here, we're running through the event, the three ensemble members in each case. The blue is the counterfactual from pre-industrial, the orange is the factual, and they've also got a +2 degrees of warming. That's +2 relative to pre-industrial here. And you can see there's a very clear increase in potential evapotranspiration. Precipitation was unchanged, so you might think the drought was worsened by climate change, but it turned out that the water budget was unaffected. I hesitate to show this because probably many people here have a much better understanding of this than I do, but they used a Budico diagram where the horizontal axis, this Budico index phi, is a measure of the atmospheric water demand, and the vertical axis, E over P, is a measure of the atmospheric water supply. But as you come down the axis, then that's more supply. So the supply goes up as you move down in the vertical, and the demand goes up as you move to the right. Now they've shown they calculated then for this region both the climatology over 2010 to 2014, shown down here in this cluster points, and then for the event for the drought event itself, and you can see that the drought event was up and to the right. So the drought event had increasing water demand and reduced water supply. It was a drought. But then if you look at the effect of climate change, in each case, you can see that the colors go from blue to the upper right through orange down to red. So that's moving from the counterfactual through the factual to the future. And you see the same pattern both for climatology and for the event itself. So climate change actually is making it less of a drought, according to this analysis. All right, another approach to do a storyline is to modify the input files driving an impact model known as the Delta method. So this is with another PhD student at Reading, Wilson Chan, who's co-supervised by hydrologists. In fact, so here what Wilson drove a hydrological model of stream flow on different catchments by observed precipitation and temperature for a historical drought, the 2010 to 12 drought, and then perturbed them in various ways. So this just shows one site at a place in cluster 4, which is in southeast England, a certain stream flow, and the black is the observed event, and we focus on the 2010 to 2012 period shown in gray here, and then perturbed it. And these were one of the things that the water managers, that the water sector in England worries about is the prospect of 3 dry winters. There were 2 dry winters in this drought, and they worry about a 3 dry winter scenario. So we just added a dry winter before or a dry winter after, and those indeed would have made the drought worse. This is the SSI-6, the six-month standardized stream flow index. But we compared it with climate change on top of the 2010 to 12 drought, and this is just for the same site here. And you see that this is now for discharge, and black is the reference, the observed simulation, and then the gray shading is from UKCP 18 projections of climate change, and you see under 2 degree or 4 degree warming, the the discharge drops a lot. So if you compare the 2010 to 2012 event with another benchmark event, the 1989 to 93 event over the cluster 4, which is Southeast England, this is for 3 different time scales, 6 months, 12 months, 24 months. The DB is the dry before, DA is the dry after, DP is dry pre-conditions, and you see that none of those things would have made the 2010 to 2012 drought as bad as the 1989 to 93. But if you added global warming, then indeed it's worse than the 1989 to 93 event, at least for the shorter time scale. So I think this is quite a useful way to present this. As I said, one of the supervisors, Jeff Darch, works for Anglian Water, so we do have quite strong assurance that this is relevant to the user sector. And we did have quite a bit of trouble publishing this. As you know, it's in Hess, so you can read the comments if you're curious. The editor just didn't like storylines. So in a way, Wilson had been looking at the way that water sector and streamflow had been treated in England over the last few decades. And this paper that's just come out in a Progress in Physical Geography puts the storyline approach in terms of a historical perspective, and why people, although they had moved towards probabilistic approaches and model-driven approaches, are moving back, I think, into more storyline type approaches. Okay, the other kind of storyline that's talked about is a dynamical storyline, or a circulation drivers storyline. So in this figure, what you do is you step back then from, instead of imposing a regional warming pattern, you impose a global warming pattern, like the Paris target. And then instead of imposing the detailed dynamical conditions, you just impose remote drivers. And then, so once you do this, the impact is conditional on these things, plus of course vulnerability and exposure, and you block the climate sensitivity and the greenhouse gas emissions. So in this framing, climate sensitivity isn't important for the impact, it's important for the carbon budgets. And actually, if you really believe the governments are taking the Paris Agreement seriously, this is perhaps a more informative way of conditioning than conditioning on an RCP. So why is this useful? Well, the regional circulation response to global warming, I've said it's uncertain, but that uncertainty can be usefully characterized in many cases in terms of storylines based on the uncertainties in the response of remote drivers. So this is just looking at the Northern Hemisphere cold season zonal wind at 850 hectopascal based on regression across the CMAP ensemble. So this is expressed in terms of meter per second per degree of warming. This is a paper led by Giuseppe Zappa with me 5 years ago now. And the panel on the left shows the wind response to polar amplification, to more polar amplification. So you just look at the uncertainty of the spread in polar amplification. As you can see that with more polar amplification, you get a an equatorward shift of the winds effectively. But that manifests as a weakening over Central Europe here, and a strengthening over North Africa, and a strengthening of the Pacific jet. Tropical amplification is a poleward shift of the jet, and the stratospheric vortex change is basically an NAO type signal. And these actually correspond. This was obtained by regression across the climate models, the CMAP models, but they're the same patterns you see from seasonal prediction or from single forcing experiments. So I think we have a lot of reason to believe that these are actually causal patterns. So based on those, in this paper for cold season Mediterranean drying, we found we didn't get a very clear signal from polar amplification. It's probably there, but the models don't respond always in a very similar way. Plus, I think a lot of it's mediated by the stratospheric vortex. So we use the stratospheric polar vortex and tropical amplification as our two drivers, and you see we came up with these 4 storylines of change. One is, well, for example, in the lower left, it's that the tropical, this is the upper troposphere tropical amplification of warming. I should have said, by the way, the polar amplification of course, that's uncertain because of boundary layers in the Arctic and mixed phase clouds, as well as sea ice probably as well. But certainly for the models really have a huge range in terms of things like the boundary layer, which is very important for the lapse rate feedback. A tropical amplification, you've got uncertainties in convection and clouds in the tropics, and the stratospheric polar vortex, you've got uncertainties in gravity wave drag schemes. So all of these reflect the basic driver uncertainty, reflects uncertainties in the parameterized processes that drive them and you can, and from what I've just said, the different parameterizations are pretty independent. So you can test, of course, but these tend to be pretty much independent uncertainties. So back to this figure, the combination that leads to the weakest amount of drawing is low tropical amplification and a weak stratospheric polar vortex. The combination that leads to the biggest changes is the opposite: a high tropical amplification and a stronger polar vortex. But you see that the tropical amplification is what is the main influence on the Eastern Mediterranean, and the polar vortex is the main influence on the Western Mediterranean. So you could, each of these storylines could be used to interpret observed changes and articulate multiple causal hypotheses. We've got a plural conditional framing here, which is what we were looking for. If you wanted to assign probabilities to them, you certainly could. They are defined in this case from the CMAP ensemble. You could define storylines outside of the CMAP ensemble, but in this case, we didn't feel there was a need to. And so each dot represents a CMAP5 model response of the tropical amplification. So it's this is degrees of tropical amplification per degree of global mean warming, or the stratospheric vortex. So that's meter per second per degree of warming. And all the black dots are the different CMAP5 models, and the red dots are for storylines. So if you didn't know anything else, you might just assign each of those storylines a 25% probability, if you're comfortable with that. You might not be. You might have a clever idea on why one of those was maybe preferred over the other, but at least you can be transparent about it. And the nice thing about this framework, I think, is that you can refine this in the future based on new knowledge. So, for example, somebody might show that one of these stratospheric polar vortex storylines turns out to be implausible, and you could get rid of that one. And the reason this is important for communication is because if you ask the question, for example, how much worse would the cold season Mediterranean drawing be under 2 degrees of warming relative to pre-industrial minus 1.5? So the traditional view is you would take all the different models. So this is showing the colors here with the contours are the warming. The drawing. So it's in millimeters per day, averaged over the Mediterranean during the cold season. And then you plot that versus global warming level on the horizontal axis, and versus a storyline impact, a low impact versus high impact storyline. So the storyline index basically spans the range of the CMAP models. So the traditional view would be that it would be anywhere from 0.03 to 0.15 millimeters per day at 1.5 degrees of C, and anywhere from 0.05 to 0.2 millimeters per day at 2 degrees C. Now, if you treated those uncertainties in a frequentist way, you would just say it's indistinguishable within uncertainties. But we know that's crazy. We know there'll be more drawing at 2 degrees than 1.5 degrees. And the reason why this traditional approach is wrong is because these errors are correlated, the uncertainties are correlated. So if you take a storyline view, you would say at the high impact storyline, the drawing would increase from 0.15 to 0.2 millimeter per day. For the low impact storyline, it would increase from 0.03 to 0.05, and it's distinguishable for any storyline. And all we've done here is to be conditional, and that makes perfect sense because we're talking about structural uncertainties here, systematic uncertainties, and you should not mingle aleatoric with systematic uncertainties. The other point I'll mention is the storylines, because you might say, well, everything isn't global warming level, and that's true. There's of course different kinds of forcers, aerosols, and so on. But the other thing is the different time scales. So I think it's been well recognized that 2 degrees of a transient warming is different from 2 degrees of a stabilized warming. So we looked at that in this paper also with Giuseppe and also Paolo Ceppi. So you may know, you may have heard of the rapid adjustment. That's the response of the climate system to an increase or change in climate forcing. In this case, this is just an increase in CO2, where you keep the sea surface temperatures fixed. So you can think of it as something that would emerge in the first year or first few months. So you see it's warming over land, and then there's a fast and a slow. We characterize them as fast and slow SST-driven responses. The fast is in the first 10 years after a switch on forcing. This is just increasing CO2 to 4 times CO2 instantaneously. And in the first 10 years, the upper part of the ocean responds, and that gives you these sort of patterns shown in the upper middle panel here. Over longer time scales beyond 10 years, then you get this other response. And broadly speaking, the rapid adjustment is a very small part of the overall warming. We've got here about 5 degrees of warming here from 4 times CO2. Only 10% of it comes from the rapid adjustment because it's only over land for the first part. And then it's roughly equally between the fast and the slow SST-driven responses. Now, the fact that these have different spatial patterns of warming means that they have different effects on the circulation. And this then is the zonal wind at 850 hectopascal. You can see that there is some effect from the rapid adjustment on the circulation. Then there's another effect, which is from the fast SST-driven part, and you see that for example, the North Atlantic is very much coming from this, as well as the Southern Ocean. And then there's a slow SST-driven part, which is especially important in the Pacific. So it's important to bear these things in mind. And this is now the annual mean precipitation change from the 4 times CO2 in 3 different regions. We've got Europe here, and we've got a box over Mediterranean. We've got North America, and we've got a box over California, and then we've got the southern part of South America and a box over Chile. The rapid adjustment is almost always a drying, and you see, but then the fast, you can see, for example, for the Mediterranean, about half of the drying is coming, this is annual mean though, from the rapid adjustment and half from the fast SST-driven response, and basically nothing from the slow response. This is if we believe the seamant models. Chile is even more in the fast response, but really nothing in the slow response. For California, it's the other way around. You get wetting from the slow response. So if you look at these different, then for any scenario like RCP 4.5 is a moderately stabilized one, where you have a rapid increase and then tailing off, and you can partition. It's purely a linear process here. So you can, it's not nonlinear in time, but it's linear physically. So you can deconstruct it into the fast and slow parts. And for example, in the Mediterranean, you would, and we partitioned P and P minus E over the cold and the warm part of the year. I won't go into that. But basically for Mediterranean and Chile, as soon as the warming stops, you realize the full extent of the drying that you're going to see, according to the models. Whereas for California, it's the other way around, and the warming is hidden. The wetting is hidden in a way and will only emerge from the slow part. So finally, though, just to come back to the question of societal benefit and so on, I think it's a question of justice. And in this paper with Regina, we actually were inspired by Schumacher's famous book, Small is Beautiful. He was asking at the time, how would economics look if it was done as if people mattered? I think we all know that the last 50 years have gone in the opposite direction. We asked the same question of climate science and asked how it would look if it was structured as if people mattered. And we found a lot of quotations in Schumacher that were very pertinent, and we grouped them into 3 categories. One was grappling with complexity of local situations, and we argue you can do that by expressing climate knowledge in a conditional form, specifically conditional probabilities. You also the importance of simplicity when dealing with deep uncertainty, and we can achieve that through the use of physical climate storylines. And finally, empowering local communities to make sense of their own situation. So Schumacher argued for what he called intermediate technologies. He was meaning physical technologies like waterworks and so on. We would be talking about data science methods that build trust and transparency, and causal networks, I think, are a way to do that. So finally, let me conclude. To address adaptation challenges, we really need to navigate this cascade of uncertainty and connect to the decision space. The societally relevant question isn't what will happen. If we knew what would happen, of course, that'd be great, but we don't. So we shouldn't worry. Just because we don't know what would happen, we can still provide guidance on what is the impact of particular actions on a certain regional climate change. But to do that, we need to find a scientific language for describing a plural conditional state of knowledge that exists at the regional and local scales and resist aggregation. And the storyline approach to regional climate information does exactly that. I haven't really talked about this here, but it's in the 2018 Storylines paper, linking to historical events in their proper context brings us salience to this. This is obviously important for communication. It's well understood psychologically. And also, what I think is quite important, people often talk about narratives, but what they do is they run the models and they make a narrative around the models. That's an after-the-fact narrative, which is a bit contrived sometimes. So storylines have a built-in narrative structure, actually. So it's not contrived. It's part of the analysis. But because it's a narrative, it has an emotional element, and it's been shown that that's really essential for decision making. Damasios, a neuroscientist who wrote a famous book on that, and Davies is a sociologist. So we need to explore storylines of climate risk, combining the best information from all sources, interpreted not as a prediction, but as representing plausible futures. Thank you very much.